All right. So some of what I wanted to do on Thursday, couldn't do because my files, for some reason, I wasn't able to access on OneDrive. So I think I've got that all worked out. We'll finish up some things we were talking about with data issues, and we'll then kind of move to the next topic, which is panel data. Right? So that quiz and that problem set is be kind of a weird point in the semester. We're a little bit further removed from the material that we covered. So that stuff was all over interaction terms. So we did a little bit of review of that last week, kind of thinking about interaction terms. Those are both set to be due at the end of this week on Friday, right, the 18th. So those are going to be primarily over stuff that we talked about back here. So nonlinear relationships, and then kind of, sorry, I'm confusing myself. So if we look at this problem set, right? This was primarily thinking about kind of including interaction terms. So here we've got kind of marginal effects, predicted changes for different groups. So we're getting a little bit further removed from kind of the material. Last week we talked about data issues. So those are going to be related to interaction terms. So all the data issue stuff, the only thing that was kind of fair game there is what we talked about when we had measurement error in our independent variable. That was kind of random. We said we knew we could put a sign to that bias, that attenuation bias. That's kind of the only thing that's kind of fair game for those. Okay. So as you're working on that, if you have any questions this week, got office hours Wednesday. I'll likely add some additional office hours Friday if you want to stop by Friday afternoon. I don't know exactly what time, but probably a couple office hours there in the afternoon from like 1 to 3 or somewhere around there. I have to look at my schedule, and I'm waiting on a few things to kind of solidify exactly when that'll be. But I should have a couple extra hours in the afternoon Friday if you want to stop by and kind of go through that. I know it's Easter weekend. Some of you are probably taking off early. But you can always shoot me an email if you're having questions as you're working on that problem set and kind of thinking about studying for that quiz, which you would use those sample questions to kind of prepare for. Okay. Other than that, any questions for me, logistics, housekeeping stuff before we jump into material? So we're still going to have one more quiz and one more problem set. So we're getting close to the end of the semester. So we've got what this week, we'll kind of finish up data issues, start on panel data, probably finish panel data this week, pretty short. Next week, we'll kind of talk about instrumental variables, right? That's another solution that we have to some of these issues that we've discussed with data. And then that next week, we'll be kind of maybe finishing up instrumental variables, but probably just doing review in class. So I don't know if I'll get it up by the end of this week. That's my goal, see what happens. But I think that the practice final, I'll for sure have it up early next week. So you'll have more than a couple of weeks with that. That's kind of what we'll be going over that week before the final to kind of prepare us for that. So you'll have a practice final, kind of think about the types of questions you'll see on that final exam. So really this week, right? Then next week, right? That's our kind of 2 weeks of new material, then a week of essentially review, right? And then we've got finals week, right? And I forget, does anyone remember without me looking at what's the final date for this class? I know my other one's Monday. It's in the syllabus. Looks like we're on Tuesday, right in the middle of the day. So not super early, not super late. So that's kind of good for you guys. Okay. All right. Any other questions before we jump into things here? Also, just to make you aware, that 5th problem set and 5th quiz might be a little bit kinder on them, so it might not take you near as long. So that 6th problem set, as long as we're kind of here looking at what we're talking about with panel data and instrumental variables, I'll probably have the due date set to be that week before finals, but like you'll have a lot of time with it. I'll get it up. I'm gonna finish writing it tomorrow, so I might even get it up there tomorrow, if not by the time class starts Thursday. So I have a lot of time to work with it, and they should be a little bit easier, not quite as time involved as kind of the previous quizzes and the previous problem sets, but still kind of giving you some additional material that you could also use to study for the final. Okay. All right. And you can see we have an in-class quiz today that we'll look at later. But there's no other questions for me. What we left off talking about. And I kind of went through this like example of non-response and selection bias since our data wasn't working. But really what I wanted to focus on was we had today, we'll kind of review measurement error in our dependent variable. So that was our Y variable and what that's going to do to our estimate. And then also review when we had measurement error. Where is it at? There we go. We have measurement error, classical and non-classical in our independent X variable. Okay. So we don't have a whole lot from the slides from data issues to go over, but we are going to do a lot of work in Stata. So we'll kind of start there today. Okay. And I'll reference the slides going back and forth. So here I've got my do file editor somewhere. Where is it at? Oh, here it is. Oh, I want to minimize this. Why is this being a headache for me right now? There we go. There we go. All right, so I've got a bunch of different things pulled up, but what we're looking at is going to be kind of this data issues, right? That was the do file that we were looking at last class. So I don't know, we did some of this stuff last class, and I've got some stuff thrown at the end. I'm actually going to kind of use this data issues Monte Carlo S25 to just review some of the things we talked about. It'll kind of keep using the same example, so we won't be bouncing back and forth between different examples, and I think this will kind of help us, right? So, looks like here I've got my global kind of set. The file that we'll start using is this kind of life expectancy. So let's make sure I've got my global set correctly here. I don't. Try to do it from memory. So we'll go to open. We wanted week 12 materials, which was from last week, and we wanted this life expectancy. Copy my file path so that we do things moving forward. What did I get wrong on it? Oh, I had users instead of my iDrive. That would make sense. So got my global set. You would kind of set yours here if you're using that data issues Monte Carlo file, which is, oh, did I not give it to you guys? Here, I'll drag and drop it in there for you right now. You don't really need to work along with me here. It's more of watching what I'm doing, and then I'll kind of relate it to what we talked about last week. So, but just to kind of, oh, it was there. Apparently, I just didn't add it to the homepage. So data issues. I'll add it to the homepage so it's easier to find. Under week 12. Yeah, here it is. Okay. So that's the file that I'm going to have pulled open. So the first thing that we'll do is I'm going to replace that GDP every single time we do it. I'm just going to divide it by what? A million? No. Yeah, just to make the number easier to look at, the coefficient won't have like e to the, positive whatever. So we'll replace GDP, just scaling it here. And then I'm going to run, oh, there's my global. Let's try that one more time. There we go. So we get this coefficient estimate. Very simple linear regression. I'm estimating GDP based off of BMI. This is probably, a lot of omitted variable bias, things like that. But we can see the real coefficient estimate. This is like actual data from every country. So it should be kind of like, you almost think about it like your population coefficient. Should be about what, 60,000? So I'm going to come down here. I wanted to show you, I mentioned last week, the power of what you can do in Stata. So you can run simulations, right? For other classes, other contexts, this might have some different value to you. We're just going to use these simulations to prove that if we generate random numbers over and over, some of these things that we said about measurement error are going to be true. So for this first one, I'm going to create this program. So program myreg is just saying, this is my program that I'm creating. What does this program do? It drops anything that was in memory. So we start out with a clean slate. It uses that life expectancy data set. It replaces GDP, so the coefficient's easy to look at just by scaling it. We then generate this measurement error that's just between 0 and 1, completely random. Okay. Now, when you run these, I haven't used that set seed, so you might get a completely different set of random numbers. If you want to follow along, you'll see that it doesn't matter if we run enough simulations. I was only using that set seed, so we had the same set of random numbers, and we were only doing one set of random numbers. Here, what this is going to do is it's going to generate those random numbers. Then it's going to take the original BMI variable, add the measurement error to it, which was just completely random. So my new regression that I'm running is going to be GDP on the BMI that includes that random measurement error. So we've got classical or just completely random measurement error in our independent variable. We said, what is this going to do? it should cause what type of bias? So it still should be the same sign. But if we go back, we said the estimate that we see will be the true estimate times the variance, what is this, of my x variable over the variance of my x variable. And then here we have the variance of our measurement error. So this fraction always has to be less than what? Anything divided by itself plus something is going to be less than 1. So we're always going to end up with an estimate that's a little bit low, right? Or understating the effect. So we'll actually use this to prove that this equation actually holds in just a minute. So what this program will do, so I define the program. Now, anytime I use my simulate command, I'm going to say, okay, look, run this program myreg and do it 100 times. So the reps here is 100. And this is just the syntax. I'm not going to expect you to know this or run your own simulations, but just to prove to you some of the things we talked about measurement error. Save the coefficients and the standard errors. Okay. So I'm just going to save those two coefficients, save those two values, the coefficient and the standard error, from the regressions of all 100 of these simulations. Okay. So it's going to go through this program, generate 100 sets of random numbers for the measurement error, run the regression, save the coefficient. Okay. So I'm going to go ahead and do that. Oh, I already defined the program. I already did that for you. So I'm going to go to simulate. It runs this behind the scenes, kind of tells me where it's at in the process. I'm then going to basically this simulation command, what it's done is it saved my BMI coefficient. It saved the standard error. And then it also saved the coefficient and the standard error of my constant, although we don't really write the intercept. We're just not doing that. Beta 0 is in here as well. There's nothing related to measurement error that we need to worry about that. So all we're going to be focused on is this coefficient and this standard error. Excuse me. So I'm just going to summarize that coefficient column. So notice it's got 100 different regressions. It has what the coefficient on that BMI variable was that had the measurement error included. So the average across those 100 simulations, on average, I'm seeing an estimate of about 50,000, which is lower than the original value of 60,000, right? There should be this attenuation bias. Okay. Now, I could do this 500 times, right? I can kind of do this similar thing. I've already got my function created, so it's just going to run it now for 500. Now it takes a little bit longer, right? So you can imagine if I want to do like 1,000 or 10,000, this just starts to take a while. But once again, right around that same estimate of 50,000. I could do this for 1,000, right? I should end up with an average estimate that's right around 50,000. Now we'll kind of see why in a second. Why is it right around 50,000? This one's going to take a little bit longer, so we'll wait on it, right? Sure enough, right around 50,000. So what should the estimate we see be? Well, now, if we have any one set of random numbers, like sometimes we'll see an estimate that's a little bit higher or lower than that average. But the reason why on average we're seeing 50,000 is because we know that if I use that life expectancy data, if I summarize that BMI, the original variable without measurement error, my standard deviation is 2.19, so my variance would be that squared, okay? So I have the variance of my original x variable. That was one of the things we needed, right? If we're switching over here, this was 2.19 squared. Now, we can kind of cheat because we actually know what the actual coefficient should be. That was like running it without the measurement error, right? So this is me kind of proving to you because we have the actual data and then we were generating some data with measurement error. In practice, we only have the data with measurement error. We can kind of back out what that true estimate would be if we can get an idea about what the actual X values variance was. Now, in practice, can we do that? Not unless we have another researcher that has that original BMI without that measurement error in it, right? Usually we wouldn't have that, but we know this will hold and we can kind of prove it to ourselves when we have the actual data and we generate the random measurement error, okay? Does that make sense what I'm saying there? okay? So the only other thing we need is, what's the variance of our measurement error, right? So if I go back, well, what was my measurement error? Well, I had a normal distribution with kind of 0 as my mean, variance or standard deviation of 1. Made it kind of easy, right? So I've got 1 in there is the variance of my measurement error. So I just typed that out kind of here. Now I kept it out to a few more decimals to be a little bit more precise. So I shorthanded it in the comments, but to make it a little more precise, I actually put the actual values in. So if I just use the display command to do this math for me, I should end up with a value that really close to 50,000. That's a little bit less. So if I continue to kind of run this simulation, sometimes I'll see things that are slightly above 49,752. Sometimes I would actually end up seeing some that are a little bit below it and vice versa. But on average, this should be the coefficient I find, and that's about what we were finding, right? I mean, we're dealing with rounding of decimals and things like that, so it's not going to be 100% precise. But if we kept that all the way out to whatever decimal it's stored in, we didn't kind of truncate it, we end up seeing that exact value that follows our equation, okay? Our equation for that attenuation bias, which I had right here and kind of wrote out the general form for you, okay? Now, what if I make that measurement error quite a bit larger? So here, this is my kind of standard deviation. So back here, my variance would be 100, or my standard deviation would be 10. Okay? So it's my second program. I'm just going to create another program that does the exact same thing, but the random error is a little bit more like spread out. So what should happen to our attenuation bias? So if I'm thinking about here, I've got the same underlying BMI variable, but if my measurement error is a little bit higher, what should happen to the coefficient I see? It should be lower, right? That denominator being larger, fraction smaller. I'll see. Now, with economics, like you can imagine, this matters, but we're thinking about how we measure things. You almost think about like, let's say I wanted to know the effect of height on something or the effect of weight. Well, essentially, the less and less reliable measurement tools I have, my measurement error is going to be higher, right? So like with doctors, things like that, they like use this a lot because they know all of their tools have some measurement error built in. What are we trying to do? We're trying to minimize that measurement error, right? So if instead we have a higher measurement error, we can run that simulation. It's going to save those 100 different regression results. Now, when I summarize this result, I see something that's quite a bit lower, right? Not only is it just under 50, well, it'd help if I showed you what I just did, right? So all I did was define this program, run my simulation here, so I could run this simulation again for you, summarize or kind of take the average across those 100 different random samples of that coefficient estimate. It's down to 2,500, right? Before we were at just under 50,000. And that's because the variance in our error was so much higher, right? In fact, what is the variance in our error term now? It was 100. This was telling state of the standard deviation. So if I use the display command here, sure enough, if I were to run this like 1,000,000 times, the coefficient estimate I would see would be right at 27. It's a little bit off here because we only did 100 random sets of observations, right? So we're bound to get random numbers a little bit to, either above or below that true value. But nonetheless, I think this really kind of is a good example where you see, oh yeah, the higher the variance in the measurement error, the closer our estimate's getting to 0. Any questions on that? So I'll do this one quick. If I increase that standard deviation to 300, what do you think my coefficient's basically going to be? So if the variance is getting even higher, before I had it at, what, 10 squared? Now it's going to be 300 squared. Now what do you think the average coefficient is going to be? Really close to 0, right? So if I run this, oh, what did I not do? Oh, this is a different one. Sorry. Scratch that idea. I'm going to copy and paste this then. I thought I had it in the file. I was just kind of guessing what I was going to do. So let's call this new one huge variance. So now I'm going to do the same thing, but let's even do like 1,000 here, right? So I'm going to call this new program, I don't know, myreg HV for high variance, HV for high variance. Now, if I kind of run this, I guess I didn't need this line to be copied. So now if I define this program, run my simulation again, sure enough, what do I end up with? Basically a coefficient. I mean, I'm getting really close to zero. Right? So the higher, I mean, I'll never truly get zero because that fraction has to be above something above one, but it's getting closer and closer to zero. Any questions on that? I know I'm doing a little bit of hand waving. I'm not going to make you guys run simulations on your problem sets or anything like that, but I think this kind of at least helps see in practice what I'm saying is not, you know, we're proving it with data as opposed to just relying on the formulas. Okay. So what I thought I did was the next one. Okay, now let's say I've got measurement error in my dependent variable. Okay, so this one did not just cause an attenuation bias. We weren't really sure what kind of bias this is going to create, right? Kind of depends on what that measurement error, what function it follows in terms of its randomness. So I've got one here. I'm going to define this program. We're going to do the exact same thing, but now the measurement error, I'm going to put it into GDP instead of BMI. GDP was our dependent variable. So we can do the same thing, right? Clear out the programs, run this new program, run the simulation where it runs the regression of GDP with the measurement error on now the actual BMI. So our independent variable no longer has measurement error, but our dependent variable does. So we're going to save all those coefficients, and what we see, oh, what do I end up with? Remember we said if we have random measurement error in the dependent variable, what does that do to our coefficient? Nothing. It was only measurement error in that independent variable that's kind of screwed up our coefficient. Measurement error in the dependent variable, we actually end up with the exact same coefficient as if we didn't have the measurement error. Okay. Any questions on that? So I remember right. You can also look at, so SC, okay. So let me see here. Let me do this for you. Let's say I summarize the standard errors on that. So we get a standard error of about what? 11,000. If we go back and use the variables that don't have measurement error. Oh, I have to open up the data set again. Hold on. So I'll copy this so I can actually show this to you. Here is our, oh, what did I forget to do? Scale my GDP variable so it's easier to look at. There we go. So notice my standard error of about 11,700. What was the average standard error we found when we ran all those simulations? Same value. Right? So measurement error in that dependent variable doesn't really matter. Right? That's the kind of end of the story there. Right? Doesn't matter for us. Okay. However, let's go and look at if instead, so this was measurement error that was random. So we would call this kind of like classical measurement error in the dependent variable. What if I have, so I'll run that regression again, just so we have the results. We know the estimate should be 60,000, standard deviation of about 11,000. I'm going to create this other program, which now the measurement error is random, but notice it's larger when BMI is larger, right? It's a function of that X variable. So we would say this is non-classical. So if I run this regression, I then run the simulation 100 times and summarize the coefficient. So this was measurement error that we were putting into our dependent variable. Notice, okay, there I am getting a slightly different coefficient. Okay? So if I have non-classical measurement error in the dependent variable, that does matter, right? If the measurement error of my y variable depends on the values of x, I will get different coefficient estimates. Now, which way are they going to be different? We won't dive into that, but it's going to be something about the correlation of x with y, y with the measurement error, x with the measurement. It would kind of depend on the functional form of what that measurement error is taking, right? But all I expect you to know is classical measurement error in the dependent variable, coefficients unaffected. Non-classical measurement error, it is going to be affected, right? Now, to what degree, we aren't going to dive into those issues. I just want you to know that it will be. Right? In fact, let me think here what I could do. Let's say I do the same thing. I'm going to create a new program for you real quick. MyReg5. Now the measurement error is going to be what? Higher when BMI is lower, right? If I divide by BMI. So if I run this, notice, oh, what did I do? So I get 60,088. Oh, let's see here. So I've got my measurement error. Well, I want my measurement error to be, let's say, try this. Clear programs, that's what it is. I'm going to try to give you an example if I can think of one off the top of my head just to show you. So this one actually ended up pushing that estimate to be a little bit higher, right? Not by much, but I think, right? 60,000, or was it a little bit lower still? 60,000, 60,088 compared to 60,162. So whether or not my coefficient is higher or lower kind of depends on what that measurement, non-classical measurement error is, right? But I won't, like I said, I won't ask you about whether or not you know the coefficient is going to be higher or lower. You just need to know that it's going to be different, right? Okay. So notice here, the first one was a different function for the measurement error than the second. One of those, it produced a coefficient that was lower. One of it produced a coefficient that was higher. Okay. So we don't really know. Okay. Questions on that before we keep moving here? So one example, I don't think I have one over here. So we didn't get to these either. So if you go to that data issues, so we just looked at measurement error here. You could do a very similar thing. So if we're going to scroll down to line 105 of just the original data issues do file. We can also do a similar thing. We talked about measurement error, but we also talked about just having missing data. It's a very similar idea. If the missing data is uncorrelated with your X or Y variables, it doesn't matter. If it is correlated with those, well, then you're essentially creating a selection issue, okay? And your coefficient estimate will be different. So here, I'm going to switch over, kind of clear this program out. Now, here's where I'm using a kind of built-in function. I think it was the birth weight that BQ. So one thing that we might need that's probably earlier in this, it's SSC install, all these kind of free data sets that we had. I'm going to clear my programs out so I can keep using the same names of my reg. Now, if I define this program, run the simulation, what I'm doing here is I'm randomly generating numbers, and then I'm randomly putting in, okay, if the random number is below or above a certain value, put missing. If not, what I'm basically doing is like randomly selecting, I think it's 1,000 different observations from this data set. So I'm going to have some missing data, right? I'm only grabbing 1,000 out of, oh, we can kind of look here. How many observations exist? 1,400. So I'm dropping some of them, right? So, excuse me. If I run this simulation, save the coefficients, and then look at what that coefficient is. And here I think I did family income and then birth weight. Now I had to put like this was like my randomly missing ones. So run this regression, takes a little bit of time. So we're waiting. This one's taking a little bit longer. There we go. So I'm getting kind of this coefficient estimate of 0.007. If I were to just run that regression, so we have, oh, here it is, right? Without any of them missing, this is the original data set. 0.0074. Notice if it's randomly missing data, what coefficient do I find? Basically the same thing. Now, like I said, to truly prove that you'll see the exact same value, instead of 100 simulations, you would need, in theory, I don't know how many of you, which of you are like the ultra math heads, what would I need in order to actually prove that this would be the exact same value? Infinite simulations, right? Now, the closer I get to that, the closer that value is going to get. But even with 100, we can see it's basically going to be the same value if it's completely random missing data. Now, if I instead had something, and we don't have to even run a simulation of this, if I'm just missing family income that's less than 3,000, I could just use an if statement to kind of prove if the data is not randomly missing. Well, what's going to happen there? Oh, actually, what did I do? Did I drop it? Did that drop any observations? No, that's why. So I want family income here. I guess I got to summarize it. So it's what between, oh, because 30,000 must be 30 in the data set. So if I have family income less than 30, well, now I can see, oh yeah, if I'm missing the lower half of the distribution, if it's not randomly missing, I could end up with very different coefficients, right? But if it is just completely random, we can use that simulation to prove it doesn't impact our coefficients at all either. So randomly missing data, random measurement error in our dependent variable don't impact the coefficient. Random measurement error in our independent variable causes the coefficient to be same sign, but closer to 0 or smaller, attenuation bias. Non-random measurement error, that's where we can't really say what's going to happen to the coefficient. Okay. All right. So that should kind of finish up some of the stuff we were talking about, data issues. That's what I wanted to kind of do on Thursday, where I couldn't get the files open. So make this easy here today and get this out of the way kind of early. So I've got this in-class quiz. I've got it set to be due at 2, but be done with it well. Actually, let me go back. Since everybody's here, I want to have there be value to the people who actually are showing up. So let's do 1:30. Actually, you guys can get this done here in the next couple minutes. Let's make sure that's saved. So I'm realizing I should have hit save instead of build. There we go. All right. So I'm going to walk you through this so it's not a big deal. But basically, if I'm looking at a question like this, so even though we kind of go through these, I try to just give credit for people who show up. If I were to ask you a question like this on the exam or on a quiz, which of the following measurement errors would cause an unknown bias in the estimate? So what did we just say doesn't cause any bias at all? So what type of measurement error creates no bias at all in our estimate? Classical measurement error, but in what? In the dependent variable. If it's in my independent variable, I don't have an unknown bias. If I have measurement error in my independent variable, instead, we know the measurement error will be lower, and how much lower it would follow this equation. So I'm looking for something that has a completely unknown bias. Well, as long as I have classical measurement error, if it's in the dependent variable, doesn't cause any bias. If it's in the independent variable, it causes a bias, but I know how to calculate it. And I can at least put a sign to it. I know it's just going to be a little bit lower. So classical measurement error is not going to have an unknown bias in either our independent or dependent variable. Now, we looked at some other examples where I said, even if the measurement error does depend on the values for X, so it's non-classical. Right? So if I have non-classical measurement error in that independent variable, what did that do? Well, we said there, it depended, right? One of the examples where I like multiplied it by BMI, it actually lowered the coefficient. The one where I think I did like times 1 point or times 0.5 times BMI, it actually increased it. So there, non-classical measurement error in our independent variable created a bias, but we don't know if it's going to be higher or lower. So that's going to be the one that's an unknown bias. Now, if I have random missing data, what happened to the coefficient? When it was completely random, the coefficient we found was, so that was my example where we had completely random missing data. The coefficient we found was exactly the same, right? So random missing data, random measurement error in my dependent and independent variable. All of those situations, the coefficient doesn't actually change unless the random error is in that independent variable. And even if it is, we know that it's only going to create an attenuation bias, right? We can actually put a sign and a value to it. If we have non-classical measurement error, that's where kind of all bets are off, right? We have no idea what's going to, well, I shouldn't say we don't have any idea. Based off of what we've talked about, and as far as I'm going to push you, we can't say what direction the bias is going to be. Could be higher, could be lower, we're not sure, okay? Any questions on that before we keep moving here? And I didn't put it as an option, but what would that also apply to? Not random missing data, but if we had non-random missing data, that could cause the estimate to go up or down. So like in my example, when we were just missing people that had a low amount of family income, it then changed the relationship between family income and birth weights. Well, it actually caused the estimate to be, I think it was a little bit lower. But if I'm missing data that's on the other end of the distribution, maybe it causes the estimate to be a little bit higher. We don't really know. Could still cause it to be lower. It depends what the relationship looks like at different values for X. So what would that mean? If I have different relationships at different values for X, something similar we talked about, what would that look like? So let's say, I'm trying to connect the dots here a little bit. Oh, before I do that though, let's get this submitted. So today's magic number is 500. Why? Because there's the Indy 500 Fan Fest down in the thing. I might be there this afternoon. Might be at the pub. So today's number is 500, and we said what? Non-classical measurement error in our independent variable. Okay. All right. So what I want to connect the dots for you with is with the missing data idea. Let's say I've got I don't know, family income, and I think here I had birth weights is what we were looking at. So maybe for low, thank you. There we go. So this is like, maybe there's some nonlinear relationship. So you can imagine like, if I, for some reason, tend to see this part of family income is missing, what estimate am I going to get for the relationship between this X and Y variable? Something that is negative. What if I happen to have missing data that's not random, but I'm missing high income? Well, then I'm going to have an estimate that is positive. If I were just to estimate this with all data, this is kind of a weird one, but if I estimate a linear relationship when in fact it's non-linear, what estimate am I going to find about here? 0, right? So if I run it with the whole data, just linear, it might look like it's 0, where then if I'm missing things on the left or right, it's going to completely change the sign. Now, what should I probably be doing here is estimating this as a non-linear relationship, right? But there it's a problem as well. Because if I'm trying to estimate this as a non-linear relationship, this is the actual relationship between family income and birth weights. Notice, what if I'm missing this data? Well, if I try to estimate that as a non-linear relationship, what does this look closer to? Linear. I might not actually think that it is non-linear. If this is the only, if I'm missing all the data over here, I might think I have a linear relationship when in fact, it's very non-linear. Or if I was missing higher income values, I might still think there's a linear relationship when in fact, it should be nonlinear. So missing data, I wanted to kind of connect this with nonlinear relationships because it matters when we're estimating linear coefficients and it can change the sign in either direction. But if I'm thinking about a squared term coefficient, missing data might really mess up that coefficient, right? I might actually look at the squared term and say, oh, it's 0. I don't have a nonlinear relationship. When in fact, if I had all the data and I didn't have some missing values, I might see, oh no, that squared term is definitely significant. There's a very clear nonlinear relationship here. So missing data, it would mess up coefficients not only on linear terms, the same rules would apply. It would also mess up coefficients on our squared terms. In fact, on that fourth problem set, I might have asked you guys kind of an unfair question, but I just sometimes ask you questions to push your thinking, and everyone's going to get credit for it. So there was one question. I can't believe nobody asked me about it. Was there one question on there that you guys thought was really hard, or something I maybe didn't cover in class in that last problem set? So there was something related to an omitted variable bias, and I asked you how that would mess with the coefficient on both the linear and the nonlinear term. So I don't think did I cover the nonlinear? I don't think I did, but you had all the tools to be able to think about how it would impact that, right? So the same kind of idea here, not only would something like the omitted variable bias impact a linear coefficient, it would also impact the nonlinear or the squared terms coefficient as well. Missing data or measurement error not only would impact our linear estimate, but it will also impact the nonlinear estimate. The problem there is, let's say I have this. So if I have measurement error in the dependent variable, or I have one of these like non-random missing examples, non-missing data, this, if I have measurement error in my independent variable, what is this possibly going to get closer to? Closer to 0, which might lead me to think that I can fail to reject, which would say, oh, I think the relationship is linear, even though the true estimate, right, the estimate I'm seeing is going to be the true estimate on that squared term times what? Here it wouldn't be x, but the variance on x squared plus that variance on my measurement error. Right? So all of these things that we're talking about that impact coefficients, omitted variable bias, missing data, would impact nonlinear terms as well. Now on the exam, I won't put, or the quizzes, I'm not going to push you that far. I put that problem in the problem set just to kind of get you to think a little bit harder. And I'm going to, as long as you put an answer, everyone's going to get the full, I think it was 3 points for that problem on the problem set anyways. Okay. Any questions on that idea? Okay. All right. So took me a little longer than I thought to go through the rest of that, but that should kind of finish up. We talked about selection issues, kind of hit. I won't spend too much time on this. We'll revisit this when we get to instrumental variables. This is kind of a throwaway slide for me to introduce the idea that we eventually will talk about instrumental variables, and that one other type of data error or measurement error in a way that we have is when we have like cyclical impacts. So if X causes Y, but Y also causes X, it's really hard to estimate those relationships. We actually couldn't do that without additional tools, which we'll talk about not this week, but next week. Okay. So what we're going to talk about this week is panel data. Okay. So today and Thursday, we're going to talk about a slightly different data set. We've actually looked at them a little bit already. We've kind of treated them incorrectly, although we might not have known that yet. But we talked way back at the beginning of the semester, we have like cross-sectional data, time series data, and then panel data. So if we remember what panel data was, it's when I have multiple subjects and I've collected data on them at multiple points in time. So this would be like if I had every country in the world and I had their GDP and BMI, not just in 1 year, but for 50 years for every single country. Okay? So I can follow every country over those 50 years. Right? That would be panel data. So I think the data that I'm going to use eventually and state it today is going to be test score data. So I only had a couple years. So I think it's what, 2006, 7, 8, and 9. So 4 years of data. And I had the students' test scores on. Is anybody familiar here? How many of you went to high school in Indiana? Took the I-STEP? I've got I-STEP score data. Right? You guys are probably not taking the I-STEP. No, this would have been before your time, right? So the state has it though. You can actually request it if you want to grab all the data. We're gonna have two different types of panel data sets. One's gonna be balanced, one's gonna be unbalanced. So a balanced panel data set is for every student. I have them for all 4 years. Unbalanced would be some students I have them for 2 years, some of them I have 3, some of them I have 4. So what do you think, just practicality wise, this test score data, do you think it's going to be balanced or unbalanced? What's going to happen to some students? Their parents are going to move. So they might take the I-STEP1 score, but not the next, right? Maybe it just so happened to be in 2006, that was the last year they had to take the I-STEP, right? So I'm going to have some students that have 1 year, 2, 3, 4. So I'm going to have an unbalanced data set. Right? In my country example, if I'm collecting like GDPs of countries, what is that probably going to look pretty similar to? Well, I have every country. You can go out right now and World Bank, wherever, and find their GDP measures. I'm going to have every country's GDP for the last, we'll even say 20 years to be safe. I'm going to have the same number for every country. Right? They report their GDP. So I'm going to have a balanced data set. Balanced panel data set. Okay. Now, I said last week, it kind of bled over to today. Why might we be worried about an unbalanced panel data set? So in my test score example, it might not matter as much, but let's say I'm thinking about, what would be a good one? So what issues could exist? Why might I not see some students, maybe they took the I-STEP 1 year and then they didn't take it the next, but they're still in Indiana schools. Why might they not have to take the I-STEP? Maybe they were identified as having a learning disability, right? In which case, the data that I now have on them is going to be kind of have some measurement error in it. Also, I have a selection issue of, well, who is no longer going to be in my data set for 4 years? Only, if you were never identified as having you might be you're definitely in it all 4 years. If you did have one, you might drop out halfway through. So I'm going to have fewer number of observations from those individuals than I would from someone without. Right? So I have some selection issues, right? The people that show up more often in my data set are going to have certain characteristics. Even if it's something that doesn't seem like it's as related to test scores, for sure, with my idea of parents moving, for anyone whose parents is in Indiana all 4 years, I'm going to have them in all 4 years. They're going to have 4 observations in my data set. For anyone whose parents moved, they're only going to be in my data set 1 year, 2 years, or 3 years, maybe not all 4. So how much weight is that person carrying who stayed in Indiana all 4 years? 4 observations out of however many I have. The other person's only 3 out. So the weighting is going to be different, right? So not every observation, not every student is going to carry the same weight. That could be an issue, especially when we're dealing with small data sets, okay? Excuse me. So let's think about what we're writing on here. So in any time period, so we're no longer just going to have Y and X. We're going to think about now we've got the dependent and independent variables for subject or person I. We're thinking about the test score data in time period T. So we now have to not only worry about kind of the subject, but also the time period. So there will be some relationship you could think about through Y, maybe this is the I-STEP score. And then X, maybe that is, I don't know, the student's IQ, something that's going to impact that score, right? Actually, no, let's not do score. Let's do how many hours the school prepared them for the I-STEP. So different schools might make their students prepare a higher or lower number of hours. So however many hours this student prepared or studied for the I-STEP, that's impact on their test score. However, there are some things that are just innate to student I that don't vary across time. So maybe their parents' income bracket, right, is the same over all 4 years. That gives them more resources to, be able to not have to worry about food while in school. They can focus more, we could go down the list. Maybe that factor that's constant across time is something like their innate IQ, right? It's their genetic pre-wiring. I'm not, no expert, so I'm sure like IQ, I'm sure from what I remember, it's partially like innate, but also there's like a learned component and you can like alter it, right? Because it is ultimately a test. But Z essentially will be these things that like different people are going to have different characteristics that are the same across all 4 of those time periods that would impact their test scores. So Z is going to be all of those what we call time invariant factors. So things that wouldn't vary across time. Okay. So every person's test score will be a component of the things that do vary across time, and then some of the things that don't. But those things that don't vary across time could still vary across students. That's why Z might look different for student 1 than it would for student 2. They could be in different parental income brackets, right? They could be, one student could have a birth date that starts at the beginning of the year, so they could have different ages. Right now, those ages would kind of, in terms of like when they're at the beginning or end of the school year, would stay the same every single year unless they're held back. But there are going to be factors that are time invariant as well. So the problem is, if we just kind of run this regression and we don't account for these things that are innate to the individual or they don't change across time, you can almost think about it as like Z would be part of our error term. We don't actually have data on this. So even if you think about like the underlying intellectual ability of a student, we don't truly have a measure of that. But we don't, even if we try to use a test, we don't have like their pre-wiring of how well they're going to do at some standardized tests, right? And so we can still account for those things even if we can't see them. Now, if we don't account for them, they end up in our error term. And then some of those things, like if my innate ability to learn is higher, well, what's going to happen to my I-STEP score? It's going to be higher, right? So the correlation of that error term, which now includes these time invariant factors, it might mess up my coefficient because now the expected value of my error term, which includes Z for different values of X, is not equal to 0. That was one of the conditions we need to have met, was the expected value of our error term given different values for X would be equal to 0. So if we don't have information on these time invariant factors, that's no longer going to hold. Right? You can think about it maybe this way. So I've got, skip ahead here. There we go. So here was kind of that equation with my time invariant factors. Basically, this error term picks up all of these time invariant factors. So now the expected value of my error term with Y might look different. Now, where should that be? It kind of should be built into my constant. So one way that we have of getting around this is, let's just think about, instead of like having a ton of different years, let's just think if we have two time periods. And this is the example that we'll probably end on today, and we'll kind of build on it next class. So let's say I've got 2001, 2002. Well, students, their parents can change income brackets year to year, right? Their age might change year to year. I don't know. All these other things that could change year to year are going to be captured by X here. Right? Now, they're all going to have some impact on their test scores Y. Now, the things that don't change over time, right? These are the things that we likely don't have measures on, what their innate ability, like IQ, would be. These things, Z, what's true about them in 2021 and 2022? They're the same, right? Notice there's no time associated with them. They're time invariant. So if I don't have data on these things, I don't have IQ measures for every one of the students in that data set, what's one way I can account for it? Well, we're going to do we call a first difference approach. So as long as I have panel data, I've got multiple years here, all I need is 2, really. I would take 2022's data, subtract that from 2021. So if I subtract this equation from this, this equation from this equation, notice I've got it all written out here. What's going to end up being true? Oh, I forgot something, didn't I? Where is this at? Oh, never mind. What do I want? Did I forget something here? Yes. Oops. What did I forget? So I've got, well, I skipped steps. That's why. I'm going to show you all the algebra, so it makes a little bit more sense. So if I took 2022 and I subtracted 2021, what is the equation that we would have for 2022? So this would be the coefficient for the constant, black marker, This would be the coefficient on X for 2022 plus the coefficient on that Z term plus the error, right? Now I'm subtracting from that what I would need to come up with Y. Well, Y is the exact same equation, but for 2021. Now, notice this doesn't have a time. Oops, sorry. I'm writing quick. This doesn't have a time stamp on it. And technically my error terms here would be 2022 and 2021 here. So notice this cancels. This also cancels. So when I take the first difference approach, I've got my beta 1 here. I can really think about this as XI 2022 minus XI 2021. They were both being multiplied by beta 1, so I'm just rewriting that. Everything else canceled. What am I left with here? Well, I've got this error from 2022 minus the error from 2021. I can really just think of this as like a different error term. Like it's the difference between errors, but if the errors are random, it's just going to be some new random error. So essentially, by taking this first difference approach, I've eliminated all those time invariant factors that I didn't even have data on. So if I estimate a first difference approach, I don't even need data on that. All I need data on are the X and Y values from those two time periods. I don't have to worry about all these time invariant factors. So that's helpful, right? Because when I'm trying to estimate student test score, there's a lot of, so basically what would all these things be if I didn't take a first difference? I don't have data on them, and I run a regression. So let's say I was just regressing X on Y. All the Z, if I don't have data on it, would be omitted variables, right? So what would that do to my coefficient estimate? Cause a bias. Now, if I use the first difference approach, I'm essentially, it's in a weird way, I'm accounting for those because in both time periods, they should be the same. So they're canceling out. So now, even not having those variables, they are technically omitted. But because I'm using a first difference approach, they actually are behind the scenes, but I don't even need them to run that regression. So if I use a first difference approach, I can essentially eliminate a lot of omitted variable bias. Well, what omitted variable bias can I eliminate? Anything that is time invariant. Now, if there's still omitted variables that vary with time, so like, let's say I had X2, right? And then I have what? I and 22. Now, if these things vary with time, I'm not eliminating those by using my first difference, right? All I'm eliminating is anything that is time invariant. Okay? So that's kind of where we come up with kind of this equation here, right? Now, when I was writing this out, like it looks like the constants cancel. We're always going to have a constant in the equation, even if it's close to 0. So when we run some of these regressions with this first difference, we'll see that the constant might be close to 0, but it's still going to have to exist. Just in order for us to estimate a line of best fit, there has to be some intercept, right? So it solves the omitted variable problem for everything that is time invariant. So we'll look at that do file, which was panel data. So we'll go back and show you where it's at. And this is kind of what end class here. So got what? My panel data post is the file that you guys will be using. Essentially what I have, I've got panel data class that just lets me know which one's mine, which one's the one I post on Canvas, okay? So I've got my global already kind of set. I could set it again, and then, oh, why is this not right? Oh, let's make sure that I've got it there. Week 13. Yeah, here's my first difference. So we go ahead and open that up. Oh, because this is not fall, this is spring. That would help, right? So I've got my spring file now. So I've got that first difference kind of data set opened up. Just for next class, in case I forget that I didn't update it. Get my global so it's working correctly. So I've got this first difference file. If I look at it, this is, and I might show you a little bit next class, but this is going to be a weird one where I took a panel data set, and just for the sake of this example, I turned it into what looks like a cross-sectional data set. Okay. We'll talk a little bit more next class about if I start with a panel data, how can I still use the first different approach? But just for the sake of introducing it today, let's say I've got student, so master ID is just some student ID the state gave the student. So I've got their grade size. This was like the size of their class that they were in their current grade. And then like all the third graders, all the second graders at their school. So that's going to vary with students. I've got their score in 2006, and then I had what their grade size was in 2007 and their score in 2007. So if I wanted to do a first difference approach with this data, I'm going to, if I try to just run this regression with just one time period, so just 2007, so I'm not using a first difference approach, I end up thinking that grade size has a positive impact, statistically significant, on test scores, right? Or total scores in the I-step. I think this is math and reading added together, or however they do it. And I've got a ton of observations, right? So why is this p-value so close to 0? My sample size is 630,000, right? So we're definitely going to be able to find some statistical significance. Now, the problem is that coefficient might be biased, right? Because I haven't controlled for a lot of omitted variables. Anything that would be constant within a student across time, I haven't accounted for, but I can account for that if I use a first difference approach. So what I'm going to do is create two new variables. So this variables I was interested in was how is the total score impacted by grade size? So the new variables I'm going to create are what was the change in their test score from 2007 to 2006? And then what was the difference, the first difference in their grade size from 2007 to 2006? So we're just going to use that first different approach where instead of just using y and x, we're using the change in y and the change in x. So I'm going to create those new variables. Now, why do I have half the data set missing now? Or close to half. A lot of the people that were in that data might have been in there for 2007, but they weren't in 2006, or vice versa, right? Anyone who only took the test in one of these years, I can't use them. So inherently using the first difference approach, what are we always going to do? We're probably going to see a reduction in the sample size. Unless we have a truly balanced panel data set, we're going to lose some observations. People that were only in the data set for one of these years, we can't take the difference if we don't have both years for them. Right? So we're going to have a slightly smaller sample size. So anytime we use the first difference approach, what's going to happen to the statistical significance? Even if we found the exact same estimate, the statistical significance is going to be, well, if I'm going to have a smaller sample, the most I could have is every single person was in the data set for both years. Highly unlikely, but let's say that happened. Well, there my number of observations would be exactly the same. Well, we know that some people are going to be in this 1 year, one of those 2 years. So my sample size has to be lower, which is going to do what to my test statistic or standard error? So lower sample size increases the standard error. Now that was in my denominator. If that increases, what happens to my test statistic? Smaller. My test statistic smaller, what happens to my p-value? Larger. I'm going to be less likely. I'm going to lose some statistical significance here with smaller sample size. If you don't want to go through all those steps, lower sample size, lower statistical significance, right? Is kind of what we're ending up with there. Well, if I now run a regression using this first difference approach, so the change in y and the change in x, notice now the estimate I see, it's not 0.06. Once I control for all those time invariant factors, it actually looks like having larger grade sizes does what to I-step scores? It's going to decrease them. Okay. So here, I've got a statistically significant effect. Why is this estimate more reliable? Because it controls for all those time invariant factors. Even though I don't have the actual data on them, by using the first difference, we said it controlled for all of those omitted variables that were time invariant. So we know that we're eliminating a lot of omitted variable bias here. So if we have multiple time periods, we should try to use this first difference approach. Right? Excuse me. One other thing I'll point out here, it gets kind of weird But ultimately, if I were to just look at my non-first difference regression, how would I interpret? So let's say total score is just points on the I-step. Grade size is the number of students. How would I interpret my coefficient here? Every time the grade size of a student goes up by 1, the impact on their I-step score, they would get an additional 0.06 points. Well, what's the interpretation from my first differences here? Anytime the change in my grade size is 1, so same thing. The change in my I-step score, that was my Y variable, is that it goes down by 0.01. So when we're using this first difference, the interpretation of our coefficient doesn't change. Even though we've taken these changes, that's what the coefficient interpretation was already before. So now it's a change in grade size of 1. The impact that it's going to have on my test score, or the change in my test score, is going to be whatever the coefficient is. It's the exact same interpretation. So first difference doesn't change our interpretation, but what it can change, because it controls for all these time invariant factors, is what the actual coefficient value is. We've eliminated a lot of omitted variable bias here. Okay. Questions on this before we keep moving? Okay. I want to show you one more thing, because I think I'll ask you to do this in the last problem set, but also it's just to kind of start thinking about some things that we'll start using next class as well. So how can we check to see if something's balanced or unbalanced? There's some built-in functions, I think, in Stata. We could check. We'll see next class, I believe. Let's see, do I have it down here close enough? XT set, we'll start looking at that, and there's a way to check to see if it's balanced or not. But just to kind of get at the idea of what a balanced or unbalanced panel is, I'm just going to generate this variable that's equal to 1 for every observation. Okay, so in my data set, I'm going to call it the count variable. It's just always equal to 1. Okay. What I'm then going to do is by this master ID. So this was just like the student ID number. So it's like the master ID the state gave them. I'm going to sum up that count variable and call it the total number of years, because if they're in my data set for 2 years, each one of those should have a value of 1. That should add up to 2. For any student that's only in there 1 year, when I add up all of their observations, I should only get 1. So I'm going to create that variable by each student ID, add up this count variable. That should give me the total number of years that student had in my data set. Now, we only have 2 years, so the highest it could be is 2, the lowest it could be is 1. It can't be 0, because if it was 0, they wouldn't be in my data, right? I wouldn't have a master ID for them. So I'm then going to just use the tab to kind of see, oh, okay, actually, this looks like what? Well, what did I do wrong? By sort master ID. Oh, why is this 1 for everyone here? Because I had this set up to where I had 2007, 2006 kind of stacked next to each other side by side. So it should be that I have exactly, right, every student I had in here in both time periods, it'll look the same. So this wasn't set up like an actual panel data set, but this is how we would kind of determine if it was a balanced panel data set if we had the original data. So let me see. I've got, I can do this real quick. So before I made it the first differences for today, I had, might not be right. We'll have to look at it next class. But this is basically how we'll use. So I'll do this player shot data just to show you. Oh, maybe I won't. If I can ever get my player shot data. There we go. So here I've got a bunch of different players and the number of shots they took every season. So I can do a similar thing. So instead of by student ID, I'm doing it by player ID. I'm adding up the total number of seasons they had in the data set. So notice here, I've got some players in only 1 year. I've got some players in 2, some in 3, some in 4. So here I have a very unbalanced panel data set, right? Not everybody's in this data set the same amount of times, right? Whereas up here for my first difference data set looked like everyone, innately everyone in their data set I had to have only 1 observation for. So we'll look at multiple or different data sets next class. We'll kind of keep checking them along the way to see if they're balanced or unbalanced. But that's essentially what we're doing. We're saying, does everybody in the data set have the equal number of years? If they don't, the problem is these people are going to be carrying more weight because they're in the data set 4 observations out of however many total we have. Whereas some of these players are only in there 1 out. So they're actually going to be carrying less weight than the players who aren't, or in there for 4 years. Okay. So that should be at least an introduction to the idea of panel data. We've got this first difference idea down. Next class, we'll start talking about what are some tools we have if we don't have this first difference. So like the data is not stacked, it comes in like every line is a different year. It's a little bit harder to deal with. We'll talk about some tools or some built-in functions in Stata that allow us to it's actually almost easier to deal with data sets like that, as long as we know the syntax or as long as we know the code. So we'll kind of finish up panel data on Thursday. You'll notice there's not a lot of slides, so we're probably doing a lot of work in Stata. So I've got a lot of comments, in the do file that we'll kind of be working through. Other than that, problem set and quiz due by the end of this week. If you have any questions, office hours Wednesday. And like I said, I'll post up what those additional office hours will be Friday for last minute questions. All right. See you guys on Thursday.